And now we go to the second presentation. It's Thomas Makumbi from KIT. And Thomas will speak about parameter uncertainty in the committed equivalent languages.
Thank you for the introduction. I'll speak to you about parameter uncertainty analysis of the committed equivalent land loss for intake of radon progeny underground mines. I'm from Kausura Institute of Technology, KIT, and I've been doing this work as part of my PhD tasks in work package 3, subtask 3.4. So the motivation of this study is brought about by the fact that inhalation of radon and its progeny is the leading cause of lung cancer among underground miners and indoor workers. So, basing on that, it has been found that the lung is the organ that gets the largest dose, as all the dose comes from the inhalation of the progeny rather than the gas itself. So this talk will mainly focus on the progeny for that reason. So also you should bear in mind that the lung dose following inhalation of radon progeny can be calculated by the ICRP, Human Respiratory Tract model. ICRP has developed these models to assist in the dose assessments. However, these models are based on parameters of the reference person and may not make accurate predictions from person to person. So that's why it is important to assess the uncertainties in these models. I mean the uncertainty in the dose predicted by these models, so as to better understand these models and also to investigate the influence of single parameters on the dose predictions. So this study had two aims. The first aim was to come up with a software tool that would calculate the dose coefficients, and then later on the tool would be extended to perform uncertainty and sensitivity studies on the calculated doses. So this was done using two exposure scenarios evolved by, suggested by Radonome. The first scenario was wet drilling with good ventilation, which in this talk I'm going to refer to as job type 1. And the second scenario was dry drilling with poor ventilation, which in the talk I'll keep referring to as job type 4. So in order to accomplish the study, I had set objectives to achieve. The first objective was to carry out a literature study and come up with the definitions of these exposure scenarios together with the epidemiologists from Radonome project. So the literature was subdivided into two parts. The first part, I had to review literature on the ICRP, biokinetic and dosimetric model for purposes of to be able to implement them in the software tool I was supposed to develop. And the second part had a lot to do with parameter review, and such that I come up with the probability distributions I would later use in the uncertainty and sensitivity analysis. So the second objective was to develop the first version of the software tool that predicts the ICRP, those coefficients. So having accomplished that, I had to come up with those calculations for selected scenarios in underground mines, as that is for the two scenarios, job 1 and job 4, as mentioned earlier. Then, when that was successfully done, I had to extend this software tool to be able to perform uncertainty and sensitivity studies on the calculated dose by implementing a Monte Carlo simulation. So then finally, I had to come up with a posterior data set that gives the uncertainty and sensitivities on the calculated doses, as we are going to see in the talk. So implementation of the ICRP methodology was done according to that flow diagram, whereby in the first part I had to implement and solve a biokinetic model. And the reason of doing that is that I had to come up with the number of decays in the source regions defined by ICRP, and also to come up with the excretion and retention functions, or what we call the bioassay functions. Then the number of decays was multiplied by the radiation weighted S coefficients to get the reference dose coefficients. So, and the input data was for a reference person as defined by ICRP, obtained from the ICRP publications. For example, the biokinetic models and their transfer coefficients were obtained from ICRP publication 100 for the human alimentary tract model, ICRP 137 for the systemic models of radon progeny, and ICRP 150 for the latest human respiratory tract model. Then I needed specific absorbed fractions for the dosimetric model, which were got from ICRP 133, as well as the masses of target regions in the adult male and female reference phantoms. So nuclear decay data was also necessary, and this was obtained from ICRP 107, as well as the radiation and tissue weighting factors from ICRP 10. So I implemented the ICRP methodology in our software tool, which is IntDosKit, using R programming language, and the IDE was RStudio. So R was chosen for this task since it's good for statistical computations, and also later it proved advantageous when I was performing the statistical analysis on the generated posterior distributions. So I implemented the ICRP methodology on radon progeny and other nuclides, and the results you have there are for the radon progeny, and the tool proved reliable in that it could reproduce ICRP dose coefficients with accuracy of plus or minus 6%, as you can see, for both adult male and female. So the results of the tool development and its validation can be got from our publication, Health Physics, which is shown on this slide. So then later on, like I mentioned, the second literature review was aimed at getting the parameter probability distribution. So from the exposure scenarios I mentioned earlier of job 1 and job 4, we had to come up with the aerosol properties that characterize these distributions. And these were mainly obtained from the work of James Marsh. As you can see, for job 1, for instance, those were the aerosol parameters that characterize job 1. I have the central values that were used later on in the dose calculations for selected scenarios, and then the probability distributions on these parameters, still also from James Marsh, that were used later on in the uncertainty and sensitivity analysis studies. So what distinguished between these two jobs are the parameters, aerosol parameters highlighted in those red rectangles, as you can see, for job 1 and also for job 4. So a thorough literature study was done on the probability distribution of these model parameters, and the data was compiled and published in this publication in the Journal of Environmental Radioactivity. So these publications are available on the Radonome website. If you're interested, you can have a look at them for further insight. So next, I had to perform those calculations for selected scenarios, and these were the reference doses for these scenarios, calculated using central values I showed you earlier in the tables for the parameter exposure scenarios. So mainly, I was interested, not only me, but also Radionom as well, in the doses to the lung and its various target regions. That is the bronchial basal cells, the bronchial secretory cells, the bronchiolar secretory, and the alveolar interstitial regions, as you can see, for both job 1 and job 4. So, since the lung was the critical organ, further information in this talk will focus on the lung. However, doses to other organs and tissues were also required, but calculation of uncertainty on them was not mandatory. However, I did make the calculations for uncertainties to these target organs and tissues as well, as you can see in this table. But however, here I only have the reference doses for the scenarios. So from that table, you can see that the lung doses are several orders of magnitude higher compared to the systemic organ doses, and the highest dose occurred in the bronchial secretory region and the lowest in the alveolar interstitial. So the doses in job type 4, that is dry breathing with poor ventilation, were higher than those in job type 1 due to exposure conditions in the mine for this job type that is characterized by poor ventilation, meaning it has a higher equilibrium factor and therefore higher radon progeny concentration. So that explains the higher doses for this job type. So what does that imply? It implies that the miners who are performing job 4 are more at risk of radiation-induced illnesses like lung cancer. So having done that, I had to perform uncertainty and sensitivity analysis on these calculated doses. And this, like I mentioned earlier, was done by implementing the Monte Carlo simulations in the tool. So I had to modify the first version of IntDose Kit, the software I use, such that it's able to incorporate the Monte Carlo loop for performing uncertainty sensitivity studies. And the methodology for that is summarized in this diagram here, whereby for each run of the Monte Carlo, I would sample parameter probability distribution, parameters from their respective probability distribution, and for a given set of parameters sampled, I would incorporate it into the ICRP methodology explained earlier to get the doses. This was done with random sampling, and I had to make about 50 iterations for each data set. So the result of the Monte Carlo simulation is the posterior distribution of the dose, and this posterior distribution consisted of two parts. The first part had posterior distributions for the bioassay functions as well as the number of decays, and also the second part had the posterior distribution for the dose which I was mainly interested in. So these distributions were statistically evaluated to come up with the information on uncertainty due to variation of all parameters, which you could call the global uncertainty analysis, and also the uncertainty when a particular parameter of interest is varied, which is the idea behind the sensitivity analysis. So that was successfully accomplished, and the code was tested using the information of puncher and for uranium ingestion, and we found out that the code actually would reproduce puncher values with a deviation of plus or minus 3%. So this was the testing, and the methodology behind Monte Carlo was published in this publication in Radiation Physics and Chemistry. So the main challenge, however, I encountered when implementing the Monte Carlo with random sampling is to decide on how many iterations you need. So Statistically, this was accomplished by using the central limit theorem. Statistics know that better. I won't go into the details. But however, that helped me generate the number of runs. So theoretically, I would need about 100,000 runs according to the central limit theorem. But the challenge I had that these runs would take a lot of time to generate the data set. So I had to come up with a suitable compromise between the numerical accuracy of my results and the computation time required. So what I did is that I followed the variation of the ESD, as you can see on that graph, for every 500 runs until it reached a point whereby we had to agree with my academic supervisor that if the variation in the ESD falls within the range of plus or minus 0.2%, that is enough accuracy. So there would be no need to continue the runs up to 100,000, although that would be better for the numerical accuracy, but again, it would be of no much value to the variation in the ESD, which predicts the uncertainty. So for that reason, as you can see, beyond 2,500 runs, the ESD doesn't vary much. But however, to come up with a reasonable accuracy, I decided to take 50,000 runs such that I don't compromise so much on the numerical accuracy. So this graph shows you the variation of the ESD that guided me in the choice for my number of iterations of Monte Carlos. So that was done, and the results are presented in this diagram, which shows a grouped box plot for both job 1 and job 4. So on the legend, you can see the blue box plots are for job 1, and the orange box plots are for job 4. As I mentioned earlier, you can also see it here that doses for job 4 are higher than those for job 1 by around an average factor of 1.3. And since I was mainly interested in the lung, the box plots that show the distribution of the lung and its various target tissue doses are the ones I showed highlighted in the red circle, and they appear to be several orders of magnitude higher than those for the systemic organs. Reason being that the progeny have very short half-lives, and many of them decay in the lung before being cleared to the systemic organs and tissues. So I performed a hypothesis test to distinguish between the two job types, and it turned out that the two jobs were actually statistically different, with the difference being significant, as you can see in this forest plot given by the man with test. So later on, I had to insert a probability distribution on the data set. As you can see, the log normal distribution turned out to be the one capturing the data set very well for both job 1 and job 4, and the normal didn't really do well. So from the comparison, I came up with the following conclusions: that for job 1, it follows a log normal distribution with a geometric mean of 47.05 and ESD of 1.58. Likewise, job 4 had a geometric mean of 61.87 and ESD of 1.6. Highest dose occurred in the bronchial cell and highest uncertainty in the AI region, as you can see there. So the sensitivity analysis was done by using a calculation approach whereby I would vary a parameter of interest, keeping all the other parameters constant, but to get a relative difference between the other parameters, I would also keep the parameter of interest fixed and vary all the other parameters. That shows the column other for each of the parameters. It was done for parameter groups like the deposition parameters, absorption, and particle transport, and it turned out that the activity parameters of particle deposition, which include tidal volume, breathing frequency, and breathing rate were more, the dose was more sensitive to those parameters for both job 1 and job 4 in the grouped box plot. And then among these activity parameters, still I carried out another sensitivity, and it showed that the tidal volume had the greatest influence on the lung dose, as you can see. So in my conclusion, the software was developed which was used for this task, and this was reliable for the task at hand. So improved ventilation, as seen for the doses for job 1, can reduce the lung dose by 36% approximately. So relying on ICRP dose coefficient is likely to lead to an estimation of the lung dose, underestimation, and therefore it's better to adopt the higher percentile doses, as maybe for protection purposes they could replace the ICRP reference values. So cleaner mining practices promote safer operations in the mining industry, which is in line with SDG 7, and respiratory protection and optimized work cycles are essential for high-risk jobs. Thank you for your attention. In case you want further discussions on this work, you can reach me out on that contact. Thank you for your attention.